Okay, let's unpack this. Today we're doing a deep dive into space physics. Got a stack of articles, notes here, charting its whole journey.
Right, the science of what's really going on out there
Yeah,
beyond the blue sky.
exactly. And our mission, for this deep dive is to sift through these sources, understand the big steps forward.
And see why studying this space environment, it's not just like academic curiosity. It actually matters right here in your daily life.
Totally. Because the main thing these sources keep hitting on is that space. It's not empty. Not at all. It's dynamic, full of energy.
Wild is a good word for it.
Yeah.
And yeah, our understanding came in fits and starts, some real surprises along the way.
So maybe let's start with the basics. What is space physics, fundamentally?
Well, okay, think of it as the physics of plasma, but in space. You know plasma, sometimes called the fourth state of matter.
Right. Super hot gas where the electrons are stripped off the atoms.
Exactly. So space physics looks at how that charged stuff moves around, how it interacts with magnetic fields, electric fields, especially, around Earth, near the sun, through the solar system.
Okay, so less about distant stars and galaxies, more about the charged environment closer to home.
That's a good way to put it.
Yeah.
And it's crucial because it's the bedrock for things like space weather.
Ah, space weather. We hear that term a lot now.
Yeah, and understanding planetary magnetospheres, those magnetic bubbles around planets and, well, the whole Sun-Earth connection, solar-terrestrial interactions. It sounds far off, but it's really not.
And that relevance, it really kicked off right at the start of the space age, didn't it? These sources point to 1958 as a massive year.
Oh, absolutely. Huge year.
So let's go there. 1958, Explorer 1, the first U.S. satellite, goes up, and Dr. James Van Allen's team finds something big.
They did. The Van Allen radiation belts.
What were they seeing exactly?
What their instruments picked up were these two distinct zones. Think like giant donuts wrapped around the Earth.
Yep.
And they weren't empty space. They were jam-packed with high-energy charged particles, mostly electrons and protons. And they're basically trapped there.
Trapped? By what?
By Earth's magnetic field. The particles sort of spiral along the magnetic field lines, bouncing between the poles, drifting around the planet.
Like cosmic flies caught in a magnetic web.
Huh, yeah, something like that. And the significance was, well, massive. First off, it just completely shattered the simple idea that space near Earth was a vacuum.
Right, it wasn't empty.
Not even close.
Yeah.
It showed this region is dense with energetic particles, which also meant space was potentially dangerous in ways we hadn't fully grasped.
Okay, so suddenly space has weather and it's potentially hazardous.
Exactly. And it was the first major insight into the structure of our magnetosphere, this huge magnetic bubble we live inside.
And that had practical implications right away.
Immediately.
Yeah.
Knowing where these high radiation zones were helped engineers plot safer routes for the first astronauts, the Apollo missions.
Yeah.
They had to plan their trajectories very carefully to zip through the most intense parts of the belts as quickly as possible or avoid them.
Wow. So right from the get-go, space physics was tied into safety, engineering, just making spaceflight possible.
Absolutely.
Okay, still in 1958, another huge idea surfaces, but this one started purely as theory, and apparently it wasn't very popular at first.
You must mean Eugene Parker and the solar wind.
That's the one. Tell us about his idea. What did he figure out?
Parker was looking at the sun's corona, its outer atmosphere.
Yeah.
We knew it was incredibly hot, millions of degrees, way hotter than the surface below it, which was a puzzle in itself.
Yeah, that's weird.
Right, so Parker used math, hydrodynamics, basically fluid physics, and argued that this superheated gas couldn't just sit still. It had to be constantly expanding outwards.
Blowing off the sun.
Continuously.
Yeah.
A stream of charged particles flowing out into space all the time. He called it the solar wind.
And people didn't buy it.
Oh, not at all.
Yeah.
The leading experts at the time were deeply skeptical. It flew in the face of the accepted view of a static solar atmosphere extending into space. Some apparently ridiculed the idea quite harshly. His paper almost didn't get published.
Ouch. That must have been tough. How did he get proven right?
Well, space exploration did it for him. A few years later, in the early 60s, spacecraft like Mariner 2 flew out beyond Earth.
Okay.
And their instruments measured exactly what Parker had predicted, a continuous flow of charged particles streaming out from the sun. Direct proof.
The data didn't lie.
Exactly. And that confirmation, it completely changed how we understood the sun and its influence on the whole solar system, what we call heliophysics. The solar wind became like a fundamental piece of the puzzle.
Essential for understanding comets, planets.
Everything. And absolutely foundational for space weather science. And, a really nice tribute, decades later, NASA named its mission to actually fly into the sun's atmosphere after him, the Parker Solar Probe.
That's an amazing story. So, okay, we've got particles trapped around Earth and this constant wind blowing from the sun. How do these things interact? That brings us to magnetic reconnection, right? That sounds important.
It's absolutely central. It's how energy gets explosively released in space.
Hmm.
Imagine magnetic field lines. They're everywhere in space plasma. Think of them like stretched rubber bands holding energy.
Okay.
Now, if you push together field lines from different magnetic regions, sometimes they can break and then instantly snap together in a new way, reconnect.
Like rewiring the magnetic circuitry.
Kind of, yeah.
Yeah.
And when they snap into that new lower energy configuration, all that stored magnetic energy gets released. Suddenly.
Into what?
Into particle energy, accelerating particles to incredible speeds and into heat, making the plasma hotter.
And why is that so important?
Because this process, magnetic reconnection, is the engine behind some of the most powerful events out there. Solar flares on the sun.
Reconnection.
Coronal mass ejections, those giant solar eruptions.
Reconnection again.
Yep. And closer to home, in Earth's magnetosphere, it drives something called geomagnetic substorms.
Okay, and like the solar wind, was this initially just a theory?
It was. The basic ideas, the models, came about in the 60s from people like Sweet, Parker, Yes, him again, and Petschek. But actually seeing it happen, measuring the fields and particles changing right at the reconnection site, that was incredibly tough. For decades.
So how did we finally nail it down?
That took some very clever modern missions. Specifically, NASA's MMS, the Magnetospheric Multiscale Mission, launched in 2015.
What did MMS do?
It's 4 spacecraft flying in a really tight pyramid formation. The whole point is to fly right through regions where reconnection is expected to happen in Earth's magnetosphere.
Did they catch it?
They did. They got the first really high-resolution definitive measurements inside a reconnection event. They saw the magnetic fields breaking and joining, saw the particles getting shot out. Exactly as the theories predicted, it was a huge confirmation.
Wow. From theory in the 60s to direct observation decades later. That's amazing. And you mentioned substorms. Those are linked to the auroras, right? The northern and southern lights.
That's directly linked.
Yeah.
Those beautiful lights are basically the visible fallout when energetic particles, often energized by processes like reconnection, slam into our upper atmosphere.
Okay.
And figuring out the exact trigger for the really bright, sudden bursts of aurora, the substorms, was the goal of another key mission, THEMIS, launched in 2007.
THEMIS. What was its strategy?
THEMIS stands for Time History of Events and Macroscale Interactions During Substorms. Bit of a mouthful.
Huh, yeah.
It used 5 identical probes. They were spread out at different distances in Earth's magnetic tail, the part of the magnetosphere stretching away from the sun.
The magnetotail, right?
Exactly. The idea was to track how energy, built up from solar wind interacting with the magnetosphere, gets stored in that tail and then suddenly let loose to power the auroras.
So what did THEMIS discover? What's the trigger?
It nailed it down. THEMIS showed conclusively that these substorms kick off with a magnetic reconnection event happening way out in the magnetotail,
How far out?
roughly 20 times the Earth's radius away. So pretty distant.
Okay.
Reconnection happens out there, releases energy, and that energy travels inward along the magnetic field lines, dumping particles into the atmosphere over the poles just minutes later, creating that sudden brightening of the aurora.
20 Earth radii. That's really far. So reconnection way out there causes the light show down here. Why was pinpointing that so significant?
It really clarified the whole sequence of events. It dramatically improved our models of how energy flows into, gets stored within, and is then released from the magnetosphere. And understanding that energy flow is critical not just for auroras, but for how satellites in orbit might be affected by these energy injections.
Right, brings it back to the practical side again. Which leads us perfectly to the cutting edge, the mission named after Eugene Parker, the Parker Solar Probe, launched 2018.
Yeah, this is really pushing the envelope. Flying into the sun's corona.
Which seemed impossible for so long because of the heat.
Exactly. Extreme heat, extreme radiation.
Duh.
But Parker Solar Probe is designed with this incredible heat shield and systems to survive getting closer to the sun than anything ever built. It's flying through the outer corona.
And what are the big questions it's trying to answer? Still related to Parker's original work.
Very much so. 2 main puzzles. First, why is the corona millions of degrees hot when the surface below is only thousands? That's the coronal heating problem. It's like the air above a campfire being hotter than the embers.
Still seems backwards.
It does. And second, how does the solar wind get accelerated? It starts relatively slow near the sun and becomes this supersonic flow by the time it reaches Earth. what kicks it into high gear.
Okay, fundamental questions, and it's been making passes closer and closer. What's it finding? Any
Oh
surprises?
yeah, big surprises already. Maybe the biggest is something called switchbacks.
Switchbacks, what are they?
They're these sudden, really sharp S-shaped kinks or reversals in the magnetic field lines embedded in the solar wind, very close to the sun.
Like the magnetic field is doing zigzags.
Exactly. We really didn't expect to see them quite like this. Scientists are still actively debating how they form and what they mean, but they seem linked to energy release, maybe tied to both the heating and acceleration questions.
Huh.
And of course, it's giving us the first ever direct measurements of the electric and magnetic fields right there in the corona. Unprecedented data.
So these switchbacks, this new data, what's the future impact?
Parker Solar Probe is forcing us to rethink our models of the sun's atmosphere and the solar wind's origin.
Hmm.
Understanding the source is key because the sun drives space weather. Better understanding means, hopefully, better predictions of flares, CMEs.
Which brings us back to space weather again. It feels like all these threads, Van Allen belts, solar wind, reconnection, substorms, Parker Probe, they all kind of converge on this idea of space weather science.
They absolutely do. It emerged as a distinct field because, well, we became so reliant on space technology. Think about it. GPS navigation,
Need satellites.
communications, phones, internet,
Satellites again.
weather forecasting, banking systems, using satellite timing signals. It's a huge list. As that dependence grew, especially from the 90s onwards, we realized we had to understand the environment those satellites operate in.
So it wasn't just abstract science anymore. Big solar flares or CMEs could actually cause problems down here.
Big problems. When a blast of energy and particles from the sun hits Earth's vicinity, it can mess with satellite electronics, cause radio blackouts, disrupt GPS signals by disturbing the ionosphere.
The ionosphere, that layer of the atmosphere.
Yeah. And intense events can even induce electrical currents and power lines on the ground. There have been cases of large-scale blackouts triggered by geomagnetic storms.
Seriously? Wow. So space weather isn't just about satellite problems, it can affect the power grid too.
It can. So predicting it became crucial. Space weather moved from pure research to an applied science. Agencies like NOAA in the US, ESA in Europe, they now monitor the sun and the space environment constantly.
Like a weather forecast, but for space conditions.
Exactly. They issue watches and warnings for solar flares, geomagnetic storms, radiation events, trying to give operators time to protect satellites, stabilize power grids, maybe reroute airplanes flying polar routes. It's about mitigating the risks to our technological infrastructure.
So wrapping this up, we've traced this amazing path from just realizing space near Earth wasn't empty with Van Allen
To understanding the sun's constant outflow with Parker,
figuring out the explosive engine of reconnection,
linking that to the auroras with THEMIS,
pushing right up to the sun with Parker Solar Probe.
and seeing it all come together in the practical science of space weather forecasting.
It really underscores how exploring out there, understanding that environment, has these incredibly direct impacts on, well, on you, the listener, and the technology you use constantly.
Absolutely. It's a story driven by curiosity, yes, but also by increasingly sophisticated technology allowing us to probe these invisible forces. And the discoveries keep reinforcing how connected we are to the sun and the space around us.
And it makes you think. With missions like Parker Solar Probe finding totally unexpected things like switchbacks,
Yeah.
what else is out there?
Right. What other surprises does the space environment hold? How much more is there to learn about this seemingly empty space that's actually buzzing with activity?
And how might those future discoveries change our understanding or even our technology again? Something definitely worth thinking about. Well, this has been fascinating. Thanks for joining us on this deep dive into the major milestones of space physics.